Hi, I'm Nick Stephen, and I'm with Roch Bourbonnais, and I'm here to talk about Sun Storage, OpenStorage appliances and the 7000 series, and some of the performance that we have on these new products. So, can you introduce yourself, please, Roch?
Yes. So I'm Roch Bourbonnais. I'm the principal engineer for the for the OpenStorage performance aspect, and so I've been involved in this project for going back to what ZFS was before the 7000 storage line ever was conceived. And so that naturally brought me to look at those performance aspects during engineering to make sure that as the product came out, it had the absolute best performance it could have at the time.
Okay, so thanks. So you've been starting from ZFS and working on the appliance. So the appliance came out of having ZFS, is that right?
Yes, absolutely. So we did have ZFS and obviously all of Solaris Stack and all the components of a NAS appliance. We just didn't package all this together in a product. So when the engineers at Fishworks realized that we had all these and we could really make a killer product here, they decided to go and package all this. And I was already working closely with the ZFS team at the time, driving improvement. Any novel product like ZFS obviously came out at an incredible number of features, but performance aspect needs to be kind of monitored, studied to see where performance can be improved. And I really look at performance, not necessarily people like to say yes, no, bad, good performance. Performance is mostly about what trade-off you're implementing. So you're really looking at what are the workloads that you want to care that are higher value, and is the code implementing the trade-off that you really want in a file system.
So can you tell us a bit more about, so you put together the ZFS and Solaris and Sun's hardware and packaged it up, and we've made a storage appliance. So what did we do that's special that makes this appliance better than other things?
Yeah, good question. Very good question. So exactly, we had everything, but what was the product? That was just packaging. Well, it's one hell of a good packaging. So one of the key technology we had on top of ZFS, obviously, we had all the hardware. We had, the TCP/IP, the NDMP, all the technologies required. We had the CIFS server to serve Windows clients. All this was there, but and one of the great technology we had obviously was dtrace, and dtrace just opens up our ability to look into those systems to see what's going on, because a lot of people managing NAS appliance will have to manage the performance. Sometimes it's going to work, and sometimes things not going to go as good as people expect. So having the introspection that dtrace gives you, dtrace being this amazing technology where you can go inside the system as it's running and in real time with very little intrusiveness into the OS, you can go and look what's going on at different level, at the file level, at the network level, disk level, CPU, and all put these into perspective and know, hey, this client is giving me a bad response or too much load where we didn't expect this. And so you can diagnose those things totally in a way that is totally revolutionary. So the Fishworks engineering team, one of the things among the very many things they did was to produce this analytics tool to give you this vision of what was going on. On top of that, they built a killer GUI or user administrative model that basically gives anybody the ability to administer those systems. Even though it's all based on OpenSolaris, you don't need to have any Solaris expertise to actually develop or work on those systems and administer those systems.
Okay, thanks. I certainly know that sometimes I've seen file servers that are slowing down and we don't know why, and sysadmins, they do TCP dump to find the cause. Okay. And analytics is about 7 orders of magnitude better than that. It's really easy. Just click and it tells you what's wrong. It's impressive. So this is about packaging. You've talked about software packaging and the good stuff that we have at Sun that we've put into the software. But we've also done some specials in the hardware to make this a killer appliance. Do you want to talk a little about that?
Okay. Yes. So there's software, there's obviously new hardware. So one of the mantra that the team had there was we wanted to deliver a good price performance story. So we're packaging these NAS appliances based on the inexpensive SATA drives that go at mechanically, slower speed, at 7K RPM drives. So those are a lot more economically sound, and they don't stress the mechanics. So they cost less power, good price performance in terms of power, etc. But we also at Sun, obviously, we had all those mid-range servers that are already developed and selling, independently of all this. So those are developed. We've got systems with, up to 128 gigabytes of RAM, and we've got ZFS as a storage controller, which is both a volume manager, right, talks to the disk, aggregates them, and creates a RAID array around them. It's also a file system, which obviously has the ability to cache the data. And we've got those mid-range servers with up to 1 gigabyte of RAM to cache the data. So we've got all those components, we packaged it together, and we've got a really big caching controller at a very affordable price. But on top of that, ZFS actually has two interesting paths in how it delivers data to storage. Right? There's a write path that there's a much documented ZFS intent log to accelerate the synchronous writes. Mm-hmm. And this is just, the ZIL is a side to the main storage pool. And so we went on and designed solid-state devices. We talked to the solid-state device industry and said, give me a device that can go very fast for writes. Give me very fast access on writes, but I don't care about the reads. I will not. The ZIL is a structure in ZFS that is written once, and basically is only there for protection in case of a crash. So it's basically read never. Mm-hmm. And so we went to the SSD. Can you give me a drive that read performance doesn't care? We don't care about it, but on the writes, we just want to be going as fast as possible. They said, yeah, we can do that. So we've got those fast synchronous writes, the write optimized SSDs right in there. And the beauty of the ZFS architecture is that we can scale those. We can add multiple. If each one of them is able, we've measured, we clocked them at 10,000 synchronous writes per second. So clients can do 10,000 synchronous writes per second.
That's much better than before.
On a single device. And if that's not enough, because you've got a really big shop, you just stripe them and you get, as much synchronous writes as you can, up to 4 devices like this, 40,000 synchronous writes. Pretty good. Yeah. And the interesting thing also is that not everything with NFS, for instance, a lot of the workloads, interactions with clients are non-synchronous. And those totally bypass those SSDs. They're not useful for those. And when you're thinking streaming workloads, streaming is actually a pipeline of data. It doesn't need to go to the SSDs. You go straight to disk. Disks are very good at receiving streaming data.
Okay. Thanks. Because network-based storage, synchronous writes, you're paying for the network latency, and then it's got to go to the disk. And so what you're describing short circuits that just to the machine. Exactly. Doesn't need to wait for the disk. Yep. So that's pretty impressive.
Yep.
And so that's the write loads. And I can see where these so flash memory, that lets you do that. It lets you store stuff fast. Yeah. Are you using that for reads as well?
So in the reads, yeah. So I recall I just said we went and asked for a fast write device, something that we didn't care for reads. But on the read path, well, we've got a different workload, right? There you need to be able to restitute your reads, and your requirements are quite different. On the write path, you basically only need to buffer up a few seconds of writes, and then if you can store this on those SSDs, eventually it's going to make to the main storage pool in a more asynchronous manner. That's the write path. On the read path, well, you want to have a lot of data. We know we have already 100 gigabyte of cacheable memory, memory to cache your workloads, which is great. But if you're a big enterprise and you want a lot more than that, then we said, let's go and take SSDs. SSDs are interesting because they're, in between disks and memory in terms of price and density. So you can go and we asked the SSDs, can you give us something that's going to be, at that point, we don't care so much about the writing. We're going to write at them in a background process. We don't need very high speed, but we want a very slow, very fast response time on reads. We're trying to minimize the read latency when the workload is kind of bigger than 128 gigabytes and as much capacity as we can cram. And they said, yeah, that's, here's a device, 100 gigabyte per device. We can scale up to 6 of them, 500 gigabytes, basically half a terabyte of cacheable SSDs, which gives you about 10x the latency, as seen from the client. You're going to go 10x faster.
10 times? Wow.
10 times.
Okay.
10 times faster than disk. And up to half a terabyte data. So that's a lot of random read that you can get out of that. And so what's very cool about this, obviously, is that these random reads, right, you can do, the low latency means that the people that are coming in, let's say in the enterprise in the morning, the very first guys, they're going to be serviced from those caches. Mm-hmm. They're going to get their initial queries very quick. They're going to be served very fast, and they go off before the next guy arrives. And so everybody kind of arrives and is served quickly. That's the beauty of low latency. Mm-hmm. You never get your systems in a state where you got a big queue where everybody's waiting on everybody else that was there before. If you can serve people very quickly in low latency.
So when you have lots of people, you have working sets that are different and they're not overlapping, so you need a bigger cache.
Yeah.
Bigger than RAM and cheaper than RAM.
Oh, yeah.
So with lots of different working sets, you have to put the union of all of these sets together, and you get this big caching set that you need. And RAM is too expensive, disks are too slow, and we found a sweet spot in the middle.
Exactly.
Okay, that's cool.
Yeah.
So give us some numbers.
And also, it's more interesting in terms of, right, having all this in the server, right? The beauty of NAS appliance and consolidation, right? It's obviously you consolidate your resource in one place, and you can serve hundreds of clients, and each one of those clients, if they become active, they have access to all the power, hundreds of disks, hundreds of gigabytes, half a terabyte cache. So that's the beauty of consolidation.
And inside, this is the hybrid storage pool of ZFS, and as far as the layers above is concerned, it's a file system, and it's doing all of this magic for us behind the scenes.
Yeah.
Yeah.
So and a word about, you mentioned the hybrid storage pool. That's the interesting concept here, is that the ZFS is in the middle, is only the orchestra chief saying, okay, this can go there, this can go, this is, we can stream this, so we don't need to use SSDs for that, we're going to just go to this. This is latency sensitive and not. Being a file system and a volume manager, it has a lot more knowledge than the world we used to live in, where storage was block device, file system was in a host or somewhere else, and both kind of ignored each other and didn't have the information, didn't pass the information that we can do, that we can with ZFS. Okay. So, yeah. So
you're a technical guy, I am too, but having played with this toy, this storage toy, is great. All of this is done for you. You have dials and you have graphs showing you performance. Yeah. This is all being packaged for you.
Yeah, you're a virtualization guy, so you can talk about how we package a VMware and now a VirtualBox image of this appliance, and that's been documented. Anybody can run this thing using virtualization and give it a test drive and look at analytics and see that in 5 minutes, maybe 10 minutes, you can go and configure a NAS appliance, with a 16-disk RAID pool.
That's right. You don't need to buy one of these or even have a try and buy program. You can just download an image and play with it on your desktop and see what it does. You won't see the raw performance of the physical server, but you can play with it and see how easy it is to use and administer.
Yeah.
Yeah.
And I wanted to say a word about the open aspect of this. Obviously, this is a system that is not in open source, but it is open storage in the sense that it's all based on OpenSolaris, so anybody can go and have a look at what's behind the scene, what's driving this. And it is based on ZFS, and ZFS is documented on disk format. So those disk drives that you're buying and storing, trusting your data on, is something that is done in an open way. So there's an economy that can be created around this on this format, and you are not handcuffing yourself. There's already businesses being created around ZFS, and so it is open storage in that sense.
Yeah, it's really important that it's not proprietary lock-in. it's all open source based code,
Yep.
open source standard
Open
format,
protocols.
open protocols. Everything can be reused, and you can reuse the same hardware for other stuff. You can take disks in and out and swap them around.
Yep.
Yeah, it's great. So you spend your day looking at graphs, reading numbers. Can you give us some numbers and comparisons about why is this box
Yeah.
that you plug into a cupboard somewhere better than another box
Okay.
than from what we had before?
Yeah. So, people that were, are drawn to using a network appliance storage, they don't have much of a choice today. And they've got people, they're kind of locked into proprietary solutions, and those have become very costly. So what we're really addressing here is giving you an option, based on those inexpensive storage technologies, being open, using Solaris components and hardware that Sun have. We can give you unparalleled price performance here. So that's really the draw to this thing is to look at the price performance, the other the price, the watt performance, the square foot, the performance per square foot. All these metrics are really unparalleled here. If you look at alternative solutions, they will use more expensive component at a premium, and we're using inexpensive disks, and we're thinking those inexpensive disks has greater density. There's obviously they're bigger drives, and the cost per byte is totally uncommon or cannot be compared with what the alternative has. So you can have a lot more bytes per dollar, and if you take two of our drives, right, in a mirrored configuration, well, even if they're 7K RPM drives, the two of them is 14K RPM. So you've got a response of a more expensive disk, but you're paying a lot less for that. Mm-hmm. So there's quite a lot of workloads out there that first are going to be benefit from cache. So we obviously believe that caches work, right? They work for CPU, and people, a piece of data you just use is very likely to be used by either you or somebody in your environment very quickly. So having a lot of cache is really valuable. So we think that caches work. So that's why we're designing a lot of them.
So do we have the same caching as other people, or do we have more?
We've got more RAM to cache, and we don't have, like I said, with ZFS, we don't have to go through the more expensive path. The SSDs obviously have higher cost per byte, but on our writes, we don't have to go through those paths. Okay, we bypass those for whenever you've got big streaming data. Well, you don't need to go through the SSDs. Yes, these accelerator devices are only there to help you, focus on the higher value component of your workload. Okay. And so, better price performance is number one. But because of the architecture of ZFS, there's also aspect of this that's going to make it just more pure performance. We've got streaming performance that we think cannot be matched, and we're packaging this with gigabit NICs, obviously, because only a few 1 gig NICs. We're packaging with 10 gig NIC. So 10
gigabyte networks.
Not out of 5. It's a add-on, right? It's an option, but the box can drive a gigabyte per second of read stream.
Yeah, sorry, 10 gigabits. Yeah.
So a gigabyte is more like a 10 gigabit NIC. Yeah. So that's the amount of data we can drive through this system. Okay. And in terms also of random reads, random reads, if it's going to come out of the cache, we're obviously going to be able to deliver 30, 40,000 random reads on those systems. If it's coming out of the disk drives, well, disk drives are disk drives. If you got rotation, right? We can do maybe 150 rotation random read per disks.
Per second.
Per second. Yeah. Yeah. So it's an expensive disk, right? It's not the top notch, but if you put two of them for this, you got 300 per pair. In a mirrored configuration, that's what you would be expecting.
So a lot of the time we're not. Sorry. Yeah. So if I understand with this network storage device, a lot of the time we're not bound anymore by the speed writing to the disk because we've got the SSD devices. We're bound not so much by the network anymore because the networks are going blazingly fast.
Yep.
We're not bound so much by... So we're basically looking at almost local disk speeds, and even because it's a server with lots of RAM and lots of caching, maybe even better. Is that right?
It certainly can happen, right? I mean, if you've got a little bit amount of RAM on your client, you're going to be better off working out a cache of those systems, and that's exactly right. You want the storage to not be in your path, right? You don't want to be. I did a study of Bonnie++ recently. It's on my blog, for instance, and most of the time, it's client consideration that are impacting and governing the speed of response.
So it's the client CPU.
It's the client CPUs and behavior that is causing the performance.
Pretty impressive.
And which is what you actually want, right? The storage should not be what's slowing you down. Okay.
So thanks. So we've talked about these storage appliances which are on sale now, and you can try and buy them.
Yep.
So what are you doing now? I mean, what's the next step? The NEC Plus Ultra beyond this?
Yeah, so up to now we've been looking at how can we make our code better, and we're coming to a point where we've improved our system, and we don't find any more performance improvement, the low-hanging fruit in there. So the system is behaving like we want. The next step is to characterize more at a higher level. What does that mean to people to be running on those systems? Okay. How many clients can they support? How many Exchange users? Or how many virtualized environment can they run off one of these systems? So high-level applications is what we're looking at, and one of the next big enterprise will be around iSCSI, and looking at iSCSI performance, and our initial results look pretty good.
Okay.
Thank you. So Nick, I want to show you our next step is to see I said higher level applications and how they work against the storage appliance. And so what I did was I took a virtualization environment on my Mac, and I went and ran. I'm trying to stimulate a storage system. So these are
stimulate, not simulate.
Stimulate.
Okay,
I said
sorry.
Yes.
Okay.
Yeah, I need to stimulate the I/Os. And so, a virtual environment OS running is kind of idle. And, I needed something. So somebody told me, just do a reboot. That's going to get the I/Os running. So I took a virtualized environment and I ran a reboot.
So you got our storage appliance
well, actually,
running?
No. So actually, no. So I have I only had initially on my Mac, an OS running, and I ran just reboot. I figured that's going to be generating I/Os. I went into the Mac OS, obviously open protocol. It has dtrace. Mac OS
Sure,
has dtrace.
they copied dtrace from Solaris.
They got dtrace from Solaris. And so I went into the Mac and I ran these scripts to look at what was the I/O pattern. What are the size and the time scheduling of those I/O patterns. So up to now, nothing to do with Amber Road or anything. It's just pure Mac stuff, running virtual environment, doing a reboot. Capture the I/O and import that into my system here, and this is what it looks like. So that's a little tool I wrote some time ago, and I use that for performance analysis. And what we're seeing here, what we're seeing is an OS booting, and the little bricks, those bricks here, each one represent a different I/O. And if I put my mouse pointer over it, I see it's a 40K I/O, and it lasted so long, and then that's the time. That's actually a time view of a system booting. Most of it are reads, as we expect, but there's a few storms of writes, and I don't know exactly. I don't really care what this is.
So the blacks are the writes.
The blacks are the writes, yeah, and the orange are the greens, and the other are just bookmarks because I had this. I was studying this, so I can just look at this. Now I can also just say, get me the byte stats here, and what I figured out of a boot here lasted about 100 seconds. It took 100 seconds. It had 330 megabytes of reads. during those 100 seconds.
Okay.
Not so bad. And surprisingly, somewhat surprising, 90 megabytes, about 25% equivalent of write. Maybe because it's a virtual environment, maybe because of something else. I'm not taking a stance. That's just I observed that. And so then what I wanted to replay this, and it's not so easy to replay an I/O pattern because you don't know exactly the threading model. But with my tool, I was able to extract what's the parallelism that we expect out of I/O. When those writes are going on, I know that I can, those things can do, can be parallel. They can be issued in parallel.
So you're seeing different threads calling write at the same time?
Exactly.
Through dtrace?
Yeah, that's what I eventually saw. I saw the I/O parallelism. So I wrote another tool to kind of capture those the I/O parallelism and replay those. And now I've got the ability to rerun a boot, okay, using only straight little C code, and I can run this over NFS, iSCSI, whatever, wherever, and I can scale this, right? I can run hundreds of them in parallel.
So if I summarize to see if I understood, you took XVM VirtualBox and you installed an OS onto it.
Yep.
And the virtualization platform VirtualBox lets you install an OS in a window running on top of your other host OS, and that was Mac OS.
Yes.
And you used dtrace on the
Mac
host
OS
to see what the IOs were when you were booting up that OS, and the IOs you stimulated, you recorded.
Yeah.
And now you're simulating the IOs with another program that plays them back as IO.
Yep.
And then you can use that simulation of a boot many times over repeatedly without having to reboot each time.
Exactly. And for a performance engineer, it's very important to have a reproducible workload.
Yeah.
A reboot will not necessarily be a very good reproducible workload, but if if it's canned in the way I have it, then I'm confident it's going to be the same exactly every time. And
you can presumably reboot not just one machine, you can reboot 100 machines in parallel.
Exactly. Because a boot, as we say, it's 300, 400 megabytes of total I/O over 100 seconds. Is very light load, 4 megabytes per second average load, not very intensive. So you really need, I want to verify how many can I boot simultaneously, and right now I'm estimated I can do hundreds of them, many hundreds of them, before each one starts to notice that there are other people around. So I can show you, this is really work in progress, but if I look at this trace here, it's not perfect. That's actually, on the Solaris machine, the replay of that same boot.
So here we see the same timeline with the same spikes.
The same timelines, or fairly similar enough timelines. The conjunctions of reads and writes. It's the exact same number of IOs, the exact same number of bytes, and the parallelism is not necessarily the same because obviously we're impacted by the response times that we get, which is not the exact, the same.
So here you're replaying not against the Mac, but against
Amber Road.
Against Amber Road.
So now this is running our storage appliance is there, the Sun Storage 7000 line, right? This is running in the U.S. I've got my clients there. I've got 10 different iSCSI target seen by one device, and I'm gonna just because I'm starting, I'm gonna put hundreds of them. I'm going to use 10 clients. I'm going to put hundreds of concurrently booting system in a loop, and they're going to be booting and over. But here's what we can show here. This is actually the user interface to the Sun Storage 7000 line.
Okay, so this is the administrator's interface of the storage box.
Yeah. So right now I'm not in the virtualized world anymore. I just got my web browser pointing to a system which is in this 9 time zones away, and I can monitor what's going on, and we're seeing here the network activity from the load of 10 concurrent boots in the loop.
Okay. That's amazing.
And what I find amazing, so the power here, this is just the dashboard, the monitoring thing, but we can go to analytics, and I actually save the worksheet normally. There you go, 10 Windows boot over iSCSI from a single client. And even though the system is 9 time zones away, you can see the graphs here. I'm plotting the network activity, both in and out. So as we saw, there's some reads, some writes going on. So, 40 megabytes per second out instantaneously, and you can see the very smooth draft. This is, I thought, pretty amazing that people developing this managed to deliver this thing over, such a long latency links. But we don't see this at all. This is very usable intercontinental. The disk activity are very modest at this point. Again, 10 concurrent boots at this point, very modest load on the system. And this is the hits, cache hits per second. Here, some peaks at 13,000 cache hits per second as generated by those 10 clients. But all in all, very light load. I expect to be able to boot concurrently hundreds and hundreds of machines before ever seeing a delay from the concurrency.
So this is really interesting for me because I deal with data center management. And XVM is all about data center, physical and virtual data centers, and network I/O and disk I/O is really important there.
Yeah, it's pretty cool to see.
And you're doing this from Grenoble in the French Alps, and the data center here is where is it?
That's in Menlo Park.
In the US, 9 time zones away. Yeah. So it's nice to be able to work in these snowy mountains and have our machines served from wherever we need them from.
Okay. Thank you.
Thank you.
Okay.